All right, this is the anchored boat problem, and let's read it out. A small sailing vessel with a mass of 800 kilograms. So we'll start there, make a note of that. I put the period after it so that you didn't round to 1 sig fig. So hopefully nobody did that. The anchor line is taut. There is current, which exerts a force of 600 newtons on the boat to the right. Okay, so let's start with that. We have current this way, F sub C maybe. And there's also a buoyancy force, which we're not resting on the bottom, so there's no normal force, but this replaces that, and that's acting upwards, quite a bit larger, but I'm not really drawing to scale here, so force of buoyancy. And you're supposed to draw a free body diagram of the boat in your written work. So here we are in our written work. Here's part A. And we've already got 2 of the forces. And we look at gravity, of course. So gravity should be down. If you do the quick calculation of gravity, you realize that it's quite a bit smaller than the upward force of buoyancy. So you know that your anchor line is going to have both vertical and horizontal components, okay? Though I won't be looking for that in the free body diagram because you may not have done that calculation. But force of tension in the anchor line, something like that, okay? So there's your free body diagram. And B, calculate the magnitude and direction of the tension in the anchor line. Okay, so if we look at what we have, we know the magnitude of the force of buoyancy, which is 9,000 newtons in this version of the problem. We know the mass, of course, and then we also know F sub C. We know that F sub C is equal to 600 newtons, okay? Next, well, what do we do with all these problems? Well, we do a sum of forces, and we'll use the usual vertical is Y, and horizontal is X coordinate system. And we're told that it's anchored, so it's taut, there's nothing going wrong. So we just want to assume then that, kind of like the hanging sign problem that we did as an example, that all of the accelerations are 0. And so the sum of the forces in each of those directions is 0. And only 2 forces have X components. There'll be the X component of the tension, and that has to equal the magnitude of the force of the current, right? Now I've shortcutted this a little bit, right? Normally I would write FTX negative and FC is 0, but that just leads us here, okay? And, well, we don't know an angle for the tension, but we're trying to find the tension. So what this tells us is that the X component of the tension is just 600 newtons, albeit in the negative direction, okay? And then this just being the magnitude. Okay, so that's all that we can get from this sum of forces, but we have another sum of forces, and here we have 3 different forces summing. We've got F sub B upwards, we've got F sub G straight down, and we've got some component of the tension in the line also acting down. And if we want to find the tension in the line, then we move that to the other side of the equation, and then we're just left with F sub B and F sub G over here. We know what these are. In this problem, it's 9,000 minus 800 mass times G, 9.8. And when you plug all of that in, you get something. Let's see. Okay, you get 1,160 newtons for this set of numbers. And now that you have the X and Y components of the tension, right, you have this and you have this. So this is 1,160 newtons, the Y component, and this is 600 newtons in magnitude to the left. And so we want this, though. We want the full vector, magnitude and direction. And so we can take this, square the components, right? So the square root of ftx, and that squared. If we do that for this situation, you should get about 1,300 newtons. I'll keep 3 decimal places. And in terms of the direction, well, the direction we can get a couple of different ways. I'll just find the internal angle of this triangle. So in that case, that angle right there below the negative x-axis would just be 1160 over 600, opposite over adjacent. And if you do that, you should get about 63 degrees. Okay. And if you want to put that sort of in standard notation, right, measuring from the positive x-axis, then you get 243 degrees. Okay, but as long as it's clear what direction it is in your solution, then you should be fine. For C, this is fairly quick. The anchor line snaps if after a short while the boat has 0 acceleration in the vertical direction. So in other words, it's not bobbing up and down or being launched out of the water or whatever. How does the buoyancy force compare to when the anchor line was intact? Okay. Well, a little free body diagram can illustrate this. If this is our boat again, now there's no tension in the line, right? It's snapped. So there's only 2 vertical forces. There's F sub B. There's still the current, so this thing will be accelerating horizontally for a little while anyway. And there's the force of gravity. Now I drew it to be smaller in the diagram above, but if you think about it, if there's only 2 forces in the vertical direction and there's 0 acceleration in the vertical direction, well, these 2 things have to be equal to one another, okay? And this F sub G, right, was 800 times 9.8, which is considerably less than 9,000 newtons, okay? So we know that F sub B in this situation has to be less than it was in the original situation. The reason for that is that the tension in the line, because this wasn't anchored very well, frankly, because normally you have a much shallower angle on this, usually like that if you're doing small craft anchoring, and probably other craft as well. You have a significant vertical component, and so you need to displace a little bit more water and get more upward buoyancy force to cancel that and the force of gravity on the boat. Okay, so there's that solution. We'll move on to the next one.